from Mexico, and Nikita gonna speak about the new formula for the number pi.
Yeah, exactly. So I thank the organizers for the possibility to speak here. It's a great place with great people. I liked very much the conference and everything here. It's kind of one of the best places in the world, I would say.
The level of the world.
Yes. So that's a joint work.
Much better than the previous slide.
That's a joint work with Misha Shkolnikov from Geneva. And I am now in Mexico City in San Bistav. And that's the formula. So basically that's the main content of the talk. And so this formula is very simple. You see, so we have some subset of SL to Z. And if we have an element of SL to Z, we can think it's about a pair of vectors. Yeah. Then you measure the length of one vector plus the length of second vector minus the length of the diagonal and this parallelogram. And if you sum up the squares of such a thing, you got 2 minus pi over 2. That's the formula. And the proof is very easy. I can explain it to some graduate students, high school. And I will explain you how we got this formula. Because once you obtain it, it's easy to prove it. But the story was a bit long. And by the way, we have more formulas. So you can produce a lot of formulas like that. So. Here's an important point. On the previous slide, it was square here. And with square, you have 2 minus pi over 2. But without square, you would have just 2. And also here, you also can remove squares. And you also obtain something meaningful. Great. So then we posted this question on matter flow. Okay, so here's just a question. So I put it to matter flow and ask people to prove it. Because, you know, if you have a formula, you want to have different proofs. Because our proof is elementary. And we are seeking for a complicated proof. So if you can produce any complicated proof of this formula, it would be great. Like, you know, with theory, with some group actions, I don't know, some hard measure, something. And so it became very popular on matter flow, like 71 questions, 71 votes. And that's among other very popular questions. I don't know why it's not very good to see. I can just name the questions. So here's our question. The question just below, it's periods and commas in mathematical writing. Also, it's very important. And how do I see LaTeX math in emails? Is Euclid dead? How much work does it take to be a successful mathematician? You see, it's kind of the same range. And examples of math hoaxes or jokes published on the 1st April. So it's a very important question for society, among these ones. Oh yeah, the picture was symbolize the vein. Like, you know, these people spend all the resources to build these guys, and mathematicians kind of vote mostly for these questions, how to become successful. And I start the story from the very beginning, and the very beginning is in St. Pile model. So we have some subset gamma of the square. It's just a graph. Each vertex has 4 neighbors. And St. Pile is just a collection of sand grains at these vertices. All the same as a function phi from the vertices to n with 0. And we call the vertex unstable if it has more, at least its number of neighbors grains. So for the graph, which is a subset of this square, just 4, but you can generalize the definition. So you just say that a vertex unstable if the number of grains is at least the degree of the vertex, the valency. And we can topple it by send 1 grain to each neighbor. It's kind of communistic redistribution of goods. So if you have a lot, so each neighbor can take 1. So here's example. So here you had just 1 unstable vertex. And when it topples, you have more unstable vertices, 4, 4, and 4. So just 1 toppling can produce a big avalanche in the range of the whole system. And I denote by phi null the result of the relaxation of phi.
Relaxation means.
Relaxation means that we do toppings until it's possible.
Yeah, okay.
And also you can prove that the result does not depend on the order.
Ah.
Like it's, yeah, that's it. And the model of sand piles was discovered to imitate some physical behavior, which is called power law behavior. It's, for example, when
something harmonic, yes. And then, no?
it's
Tropical limit of harmonic rate.
On lattice. No?
okay. So if you consider the toppling function,
Yeah.
which measures the number of topplings at every point,
Yeah.
it will be sub.
So,
Yeah, okay, it will be convex, basically.
yeah, yeah.
But I will talk about it later, so we will return to it. And so this model was discovered by some physicists, but surprisingly, it produced tropical behavior, which we'll see later. So now how we discovered, not we discovered, but how we proved some results about tropical curves, which were discovered by some physicists. So let's denote the maximum stable state by 3. It means that we have 3 grains at every vertex. It's stable, and if we add something, it produces avalanches. And now fix some convex domain in R2 and fix some very tiny grid, like 1/n of this square. And also we fix some points, P1 and Pn, as blue points. Okay? So our graph is just intersection of this domain with this small fine grid. And we take the maximal stable state here, means that we put 3 everywhere, and then we add 1 grain to each point here. So here it's supposed to be plus. I think it looks like minus, but it's plus.
It is plus.
It is plus, yeah. And so we just add grains to these marked points, and it will produce a big avalanche. And surprisingly, the result will be something beautiful. So we look at the relaxation of this state, and we know the deviation set is the set where the result is not 3. So we start with 3 everywhere, and deviation set is where it's not 3. So it's what changed. And experiments by some physicists, Caracciolo and others, and suggest that it will be again 3 almost everywhere, and if n is big. And we can define the scaling limit of the deviation sets. So it will be something like that. So I start with my omega as this disk, and I put just 1 point in the center. And so after the relaxation, if the grid is not fine enough, it will be something like that. So white means 3, so it's 3 almost everywhere. Green is 2, yellow is 1, and red is 0. But if you change the grid, make it smaller and smaller, then you see the perfectly defined limit. And limit looks like a tropical curve. And so a definition of tropical curve is just a corner locus of piecewise linear function. Okay? And so that was discovered by the physicists, and with Misha we proved that rigorously. Because physicists, they did not care. Now that's about your question. So we consider the number of topplings at every point during the relaxation. And now it's a proposition which I always ask people to prove, just to check that people are listening. So if the number of sand grains did not change, so we started with like 3 and ended up with 3, then we have such identity for the toppling function. So Vanya, you remember how to prove it?
Yes.
That's harmonic equation.
Yes, that's harmonic equation. But how to prove it? Is it clear for everybody?
Yes.
Okay, good. So we just count the number of incoming and outgoing grains. So this is the number of incoming grains from each neighbor, and that's the number of outgoing grains. So the function is harmonic almost everywhere, except the places where the number of grains changed. And these places, it's super harmonic. And then what is the idea of proof of this theorem is that also it's clear that the function h is integer valued. So what kind of integer valued function you know which is harmonic and as small as possible? because sand piles, they try to do less toppings if possible, so they are lazy. So we can prove that the number of toppings is the minimal possible among all superharmonic functions. And the minimal integer valued harmonic function is just linear. So this somehow explains that the actual function of topping will be piecewise linear. Where it's linear, it will be just white. It will be 3 again. And along the corner locus, it will be not 3, so it, by definition, is tropical curve. That's mainly the idea why it's true. So here's example for the circle. So that's the topping function for the circle, and that's the corresponding tropical curve. And then we started to study this object by itself. So it looks like a tropical curve, but it's infinite. So if you look at the limit, you see that it has many branching points here, infinitely many. So it branches towards the boundary of the circle. So it's infinite tree. So, and that's naturally comes as a tropical series, and here it's formal definition. So we consider any bounded convex domain, and for every latest point, we denote by Cij the minimum of the corresponding linear function. And then we consider such a linear function L omega ij, which is just ix plus jy minus this constant. What is this function? Just a function which is so here it's our omega, here it's the zero set, this Lij omega equals 0. So just support function of this direction. And then we define tropical distance function as the infimum among all these functions. And if you remember this picture with the circle, it looks like exactly as I defined here. So the actual topping function, its scaling limit, this infimum of all these linear functions. So then one can prove that its zero set is the boundary, which is natural. And now it's how we discovered P. So now we have a domain. And we have a function which is kind of integer function. So it's an integer valued. What can you count with integer valued functions? You can try to count integer lattice points inside. Okay? So now it's a very classical problem of how many lattice points do we have in a circle, inside a disk. So that's a disk.
It should be plus, yeah? It is plus.
It is plus, yeah, it is plus.
And it is plus.
Yeah, and so we have this asymptotic, and it's classical question, what is the asymptotic for E? And I think the current result are as follows, and that's the best estimates we have now. And we decided to try to apply all this technique to improve it. It's very ambitious, but at least at the end we discovered the main asymptotic. Nothing about E, but just pi. And so, yeah, so we have our function L, which is this function for the big circle of radius n. And then we can just count the number of lattice points by counting the level sets. So we take the set where the function is 0, it's all the points on the boundary. We take the points where we have 1, 2, and so on. So we take integer points in these level sets. Then how can we count them? So what is a typical level set? A typical level set here is some polygon, right? Because near the boundary we have a lot of linear functions, but in a compact subset inside we have just only finite number of them. And so it changed like that. So when we start here, we have just 1 point. Then it becomes triangle. Then it becomes something with 4 sides, 5 sides, and so on. And we can see how it changed. So let's suppose that we have, I try to draw something here. So here we have some polygon. And if we just consider the next one, if it's the same type, then one can prove that we add exactly the number of sides points here. So if we have like 5 gone, then here it's the same amount of points as here plus 5. So basically, in order to find the sum, we need to understand where do we have these branching points, where we have some additional sides appearing. And then we know everything. So here's the lemma. Now you see the appearance of SL to Z. Then for this for circle in the quadrant XY, there is bijection between the vertices and such quadruples of integer numbers. So for each vertex here, you have 2 vectors, which exactly the vectors orthogonal to these sides. And to each pair of vectors, we have 1 vertex. And we even know the height of this vertex.
Maybe for that argument, you need to somehow mention that it's a triple basis, right? I mean, integer basis, the parallel vectors, right?
Okay.
Otherwise, it's not 5.
Okay, so small remark. These arguments are completely wrong. So it was the idea how we discovered formula. They are totally wrong. I mean, so if you try to prove it rigorously, it doesn't like that.
But it is true, right? That is an integer basis, actually.
Yeah, the polygons
Because it's
are always
important,
smooth,
yeah.
so the corners are always smooth. And also it was the starting point of our project with Ernesto, that here we have somewhat canonical approximation of convex domain by smooth polygons. So that the corners, the direction will give the basis. Okay, there is bijection. And then we expected such a formula. Why? Because each corner somewhat produce you here a set of points. So here 1 point, then 2 points, 3 points, 4 points, and so on. So it seems like a sum of squares. And that's exactly, so for each vertex you have such a triangle of integer points. And here it's a number of points when you sum up 1 plus 2 plus 3 plus 4 and so on. So that's what we expected. And even though all the arguments were wrong, the final formula holds. So then sure, we verified it by computer, and we found that the sum of squares is 2 minus pi over 2, and sum of values is just 2. And then when you subtract this from this, you divide by 2, you got exactly p over 4.
Once again, what is f of p?
And f of p is just the height of the vertex. The value of our tropical function at the vertex.
Number of toppling on the previous
Yes.
one.
Or branching point of this, this family of polygons. Okay? And yeah, so there's a question, so what's the sum for high powers? We have no ideas, also we don't have ideas how to generalize it for high dimensions.
So you sum only at those trivalent
Yes.
vertices of the graph.
And only in the first quadrant. Like that. Because it's symmetric.
So it's.
But you essentially have only 1, 2, 3 when you look at f of p, yes? Correct?
Sorry?
F of p is either 0, 1, 2, 3. Yes?
No. F of p. So here we have a point p.
So it's the number of times
F
we
of
do
p,
this.
it's the value of the piecewise linear function at this point.
Ah,
So
So this infimum of linear functions.
okay.
it's the number of times the toppling is made, not the graph.
Yes. So f is a toppling function. Okay, so and then we have the same difficulty. When we try to estimate somehow the number of lattice points inside the circle, the main problem is to find the fraction parts of numbers. And here it's the same. So when you try to justify this formula, you should put integer parts and fraction parts everywhere. No.
Wait, it's technological stuff.
Yeah.
Otherwise, it doesn't fit. 1, 2, 3. It says wait 3 seconds. It's really written. You can read it.
Okay, great. And here the same problem. So when you try to justify this formula for the actual count of lattice points, you have fraction parts everywhere, and we cannot estimate them. Because here near the boundary you have a lot of branching points, and you need to know how many of them bigger than 1 over n or less than 2 over n and so on. So we have no idea how to actually improve something for Gauss problem. Yeah, and then we put it on matter flow, and here we have some sketch of the proof in matter flow. And then I'll tell you our proof if time permits. But here is the proof of matter flow. Here is Fedya Petrov, here is Fedya Nazarov. And you just form such two quantities, whereas xy is a projection. And then you can just, if you remember, at the first slide we had this formula for pi. It was the length of one vector plus length of the other vector minus the length of diagonal. So here it is. And here you can present it via this function phi1, phi2, and then you telescope them. And you will see that everything disappears except some terms. And these terms give you 2 and 2 minus pi over 2 correspondingly.
I'm sorry, have you already defined what is phi1? Is it the definition? Or
yes, it's the definition.
It's the definition. Okay.
And then you have such identities, and that's they introduce it to telescope. So if you have some series, you won't present it in such terms that they will telescope, they will construct everything. And here's how it's done. Okay?
Why you call it telescoping?
Because when you sum up by all these pairs of vectors x,
okay,
y,
okay.
one vector appears many times.
Okay. With different.
Yeah. Okay, so and if you want, I can explain you our proof. That's the end of slide talk.
Is it actually?
Okay, questions?
So if instead of a circle we take an ellipse, is it same formula for pi or maybe a different one?
It's not a formula for pi, so
But
I can explain our proof.
we can take the area of the ellipse and then take differently scaled lattice. Use the same argument in a differently scaled lattice. Would it be the same formula for pi, more or less? Or would there be a
Let me
formula?
explain you. So if I find the eraser,
So we give
I think it's cool below.
Nikita, should we turn off the projector?
yeah, you can.
Yeah, that's better. And now it goes. It's there, I think.
Great. We can start with any curve. So in our main example, we start with a circle. And we start with two tangents. So for the case of the circle, it was tangents in directions 1, 0, 0, 1, but generically we can start with everything. Then, how we obtain the formula? So here is the vector 1, 0, 0, 1. We add their sum, which is 1, 1, and cut the triangle by the tangents. And it happened that the area of triangle, that's exactly, so if you have here vector v, w, then this area is equal to the v plus w minus v plus w,
Ah, yes.
a square. Here you need that your vectors are primitive. And that's it. And then you automatically get the formula, because for the circle you start with a square. Its area is 1, then you cut all these triangles, and the sum of these triangles is exactly 1 minus pi over 4.
So you count the area of the difference of the
Yes.
square and this. But actually, I wasn't asking about this. I was
Okay, let me finish. And then how you get this second formula? So we have a formula for squares, and we have a formula without square. And without square is the lattice length. So the lattice length of this vector plus lattice length of this vector minus the lattice length of this vector is exactly this v plus w minus v plus w. Whereas lattice length is when you divide the Euclidean length by the length of the primitive vector in this direction. So you start with the lattice length 2, because we have two vectors of the length 1. And then it's the limit, the lattice length of any smooth curve is just 0. Because when you approach by some polygon, you divide by the directions and it goes to 0. That's why the sum without squares is just 2. And then you can do the same for any curve. So for any curve, you start with a curve and with 2 vectors here. And then you just add the sum of these vectors.
So these 2 vectors as your new lattice.
Yes. So, and from that point of view, if you want to obtain pi, you need to take some curve here in between of 2 lattice vectors, which gives you primitive with the determinant 1. Because if you start with vectors of not determinant 1, it doesn't work. You can rewrite formulas, but that's the idea.
So in other terms, so if you use this lattice and then you build part of the graph in this positive direction and take the sum of the squares of this at the values at the point, then you'll get the difference between this sector and the difference.
Yeah.
Is it true? Is it a generalization of your result?
Why do we have this quantity here for the circle? It's because when you write the equation of tangent for the circle, you get exactly such coefficients. If you have another curve, you have another equation of tangent in direction ij. That's how we obtain these formulas with b squared, d squared, and so on. So I have no answer except experimenting. Like you take some curve, you try to find a curve such that the equation of tangent in this direction will be something nice. Then you count the area here, and you obtain the formula. So I don't know if I answered the question.
More questions?
Did you look at automorphic forms or something? There should be formulas there.
You see, here it's a problem that it's just a part of SL to Z. That's it's all the vectors inside the first quadrant.
You don't.
So it's
You're not.
because if you take the vectors from different quadrants, like here and here, their diagonal is much less than their sum. So probably we should somehow normalize it, but we don't know how to generalize it for the whole group.
I see. But if yes, then there should be a formula.
Yeah, sure. Yeah, I'm working in this direction, but without any results yet.
No questions? If no more questions, well, thanks Nikita again.